Okay, thank you. So I'm Frans from Siemens Energy in Sweden, and I will talk today about the effect of high pressure hydrogen gas at room and high temperature on the mechanical performance of conventional and additively manufactured nickel-based alloys. The perspective of my talk will be industrial with the component lifing perspective. And I will show you some results from SSRT testing on hollow specimens, but I will also talk about why this is not enough and why we need to develop other testing methods to get closer to the actual service conditions of the components. So like you've seen before, this is part of this HYMEC 2 project that is funded by the Swedish Innovation Agency. And what I will talk about now is related to the power generation and heating technologies work package. And it's completely focused on Siemens Energy. We also have Cantal represented in this work package, but I will not talk about those results here today. So if we start with the application, then at Siemens Energy we have different products, but one of them is the gas turbines. And what we use this for is we basically use it for electricity production. So we connect the generator to this shaft. And how do we make it spin? Then we can go through the operating principle very quickly, where the air goes in through the inlet and it's compressed in a compressor. Then the fuel comes in and is mixed with the air and combusted to produce a hot stream of gas that is then driving the turbine, which is creating the work both to drive the compressor, and then we get the remaining work that can be used for electricity production. And today, I mean, traditionally the fuel has been natural gas, but as you may suspect, there's a drive to replace the natural gas with the hydrogen for decarbonization. And I will focus now on the burners of the gas turbine, where the fuel and air is mixed and combusted. And the loading of these components is rather complex. I mean, what is limiting the life is, I mean, first of all, it can be oxidation, that they simply oxidize. That is limiting the life. But if we're talking about the mechanical loading, the mechanical loading is coming from the thermal strains when we start and stop the turbine. So basically a form of low cycle fatigue, but thermomechanical fatigue then, because the temperature and the mechanical loading has a cyclic variation. And if we talk about the natural gas case to begin with, we have experienced that we need to have rather advanced testing methods to capture the material behavior, because the temperatures are high enough to cause microstructural changes in these solid solution strengthened nickel-based alloys that we're using. And we need advanced testing methods to capture that. And I liked what Chris said earlier today about if you want to do lifing for hydrogen, you should use materials data generated in hydrogen. So I agree with that, but at the same time, here we know that we need thermomechanical fatigue data to do the lifing. And generating thermomechanical fatigue data in hydrogen is very difficult.
Danger.
And or not possible at the moment, at least not with any standardized testing method. So we can get back to that a little bit later regarding the testing methodology. But now I want to give you some background regarding the material of the burners. For hydrogen operation, we need to use additively manufactured materials. I will not go into any details about the combustion technology, but we need to be able to have this design freedom, complex geometries. So in this case, we can produce the whole burner as one monolithic part. The material then, now this is not additively manufactured. This is conventionally manufactured Haskell X material, which is the solid solution strength, the nickel-based alloy I will be focusing on. And it has an equiaxed grain structure, no large anisotropy, and just there are some carbides, but they don't provide much strength. It's not the precipitation strength in the material. And if we go to the LPBF printer then, because that is the additive manufacturing method we use, laser powder bed fusion. We can see, as we've seen also in previous presentations, that we get the columnar grain structure and the highly anisotropic properties. And the chemical composition is within the specification for conventional Haskell X, but one difference is that it typically has a significantly lower carbon content. In the raw Haskell X, we only have a maximum limit on the carbon. Okay, and this is just to show you the loading direction of the specimens that were tested. I mean, we had a limited test scope, so we were forced to select one loading direction, and then we went for what we thought was most critical, the transverse direction to these columnar grains. Okay, the whole specimen testing method has already been introduced several times, I think. And as I mentioned, we are testing two different materials, the hot rolled Haskell X, which is also in a solution anneal condition, which I perhaps didn't mention, whereas the additively manufactured material is used in the as printed condition. So do slow strain rate tensile testing at the temperature of 20 degrees and 800 degrees. And we have an internal pressure of 200 bars and a strain rate of 10 to the -5. And we interrupt the test upon leakage, and as soon as it starts to leak, we don't have any hydrogen anymore, which is important to consider for the high temperature testing. I mean, we measure the hydrogen content afterwards, but if it spends too much time at high temperature after the leakage, the hydrogen will escape in a rather short time. So what we measure after the test could be underestimating the hydrogen content that we actually had upon leakage. And I shown here that also the internal surface roughness is kept to within the limits of, or what is expected to be the limits of this standard that is under development. And here we don't see this, we only see the room temperature tested up, but the heating would be achieved by an induction coil around the specimen. And what I want to highlight here, I mean, it's been said before that, I mean, this test method, it has its drawbacks and challenges, and usually it's said that it's a cheap, safe screening method. But from my perspective, maybe the most interesting about this testing method is that we have the freedom to go to as high temperature as we want, and also have high heating and cooling rates. So we can run, and we can also have a strain measurement at high temperature. So it's quite straightforward to use normal TMF test rig and test a specimen with hydrogen inside. Or I shouldn't say it's straightforward because I haven't done it yet, but you don't need any large investments like you would need for some other testing methods. So that is critical from my perspective to be able to get close to the operating conditions. We do need to cycle both temperature and strain. And I see this as an important complement to the autoclave testing methods where we are usually confined to isothermal testing conditions. And at least for the foreseeable future, we're also limited to lower temperatures than 800 degrees, as in this case. But that being said, I was talking previously about the component loading and how to predict the cyclic life is really our challenge. And what does a slow strain rate test really tell us about the fatigue life? It's a quite bold assumption that we can have a correlation between the ductility in the slow strain rate tensile test and the fatigue resistance. So that's why we need to be able to do fatigue testing. So if we look at the results, then, I mean, maybe for many of you in the room here, these results will probably not be that surprising. For the hot rolled Hassler X, I mean, there is data in the literature. As long as you don't have huge hydrogen concentrations in the material, it should be rather insensitive to hydrogen embrittlement. And here we see very small difference between the hydrogen and the argon tested material, both when it comes to the strength and the ductility. So if we have a look at the fracture surfaces, mostly ductile fracture. For the specimen tested in hydrogen, we can see some localized small areas of more brittle fracture, but overall quite ductile. And these areas are located close to the hole where we have the hydrogen exposure. So, and we also observe, it can't be seen here, but secondary cracking inside the hole is more pronounced when we test in hydrogen compared to argon. For the printed Hassler X, we also see very small differences, relative elongation of 94%. And yeah, the fracture surfaces look very similar in hydrogen. So if we go to the high temperature testing, then for the hot roll Hassler X material, I mean, at 800 slow strain rate, we obviously have a very large creep influence, so much lower strength, and but we do have a very large elongation to fracture, and in this case, it's actually higher in hydrogen than in argon, but I think that is mostly reflecting the scatter of the testing than anything else. And the fracture surfaces are typical creep fracture surfaces with creepoids. And the printed material tested at 800 degrees, we have a much lower elongation to fracture compared to the conventionally manufactured material, both in argon and hydrogen, and that is expected due to the completely different microstructure with this fine cell structures that we have. So it's something that, I mean, it's considered in the when we design with this material, it's already considered, and the good news is that it doesn't get worse with the hydrogen. And the fracture surfaces look quite similar in argon. So I can quickly mention the TDS measurements. We see for the hot roll Hassler X at room temperature, we have more or less no hydrogen uptake measured. We measure it to bulk measurement of the whole parallel length, so it's not surprising. But maybe we see some shift to weaker trapping sites. And when we test at 800 hot roll Hassler X, we have a clear hydrogen uptake. And this difference between these two different tests, I think it's related to what I mentioned previously, that we can get the effusion of hydrogen after the leakage, but before we manage to cool down the specimen. And the printed Hassler X tested at room temperature, we detect some hydrogen uptake. The reference concentration is lower than for the wrought material. And then we and maybe detect some uptake, and also maybe shift to weaker trap sites. Yeah, and this is the overview. I think it says basically the same that I just said. Yeah, and the conclusions are that we don't see any significant deterioration of mechanical properties due to hydrogen at any of the test temperatures for any of the materials. We have this small localized areas of quasi-cleavage, but it's not really reflected in the test results. And the lower creep ductility has nothing to do with the hydrogen, it's expected. And of course, at 800, we do have hydrogen uptake during the testing. And the outlook here is that, I mean, we need to develop the testing methods. We want to do fatigue testing of hollow specimens with the service like loading and temperature, so basically thermomechanical fatigue testing. And we also want to study the influence of aging. As I mentioned, we will get precipitation of carbides and other phases during operation, and how will this influence the hydrogen enrichment? Yeah, and last of all, characterization of the damage mechanisms. We only did basic phytography so far, but I mean, until we have a material that has been exposed in the representative way, that's when it gets really interesting to do the characterization work. Okay, thank you.